Hey there, this is Group 14 and our members include Ganjajun, Kuwanyu and Wan Abdul Rahman. In this video, we'll be discussing on the determination of caffeine concentrations by using UV-Vis. So, what is UV-Vis spectroscopy? UV-Vis spectroscopy is a measurement of the wavelength and intensity of absorption of near ultraviolet and visible light by a sample. It is one of the oldest instrumental techniques of analysis, and it is a basis for a number of ideal methods for the determination of micro and semi-micro quantities of analytes in a sample. Ultraviolet and visible light are energetic enough to promote outer electrons to higher energy levels. From there, the absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. UV spectroscopy is usually applied to molecules and inorganic ions or complexes in solution due to its broad features that can be useful for quantitative measurements. The concentration of an analyte in the solution can be determined by measuring the absorbance at some wavelength and applying the Beer-Lambert law. So, how are we going to measure UV? This is done by using a UV-based spectrophotometer. Without further ado, let's take a look at how it operates. This is the UV-Vis spectrophotometer as mentioned just now. The machine is connected to a software on a computer and the substance that is tested is chosen from the selection menu. Two of these rectangular cells, which are normally made from pure silica or known as quartz, are then classified into the sample cell and the reference cell, which is commonly known as the blank cell. They both have a path length of 1 cm. These cells coated with the substance are then placed into the equipment into their respective slots. The UV in a machine is normally produced from hydrogen or deuterium lamps and will be passed through the cells through these glass panels. The UV transmitted is then measured with detectors on the other end. The cells have to be clean and fingerprint free, hence these special wipes are used to achieve that. So what are the aims of this experiment? Firstly, we would like to identify a suitable wavelength scan for caffeine. Followed by, we would like to perform a calibration experiment using standard solutions. Next, we would like to determine the concentrations of caffeine found in beverages samples, and lastly to characterize the effect of sample dilution variations on the concentration readings produced.
Theoretically, wavelength with maximum peak is the best to use as it gives the best signal-to-noise ratio, which can improve the precision of measurement. However, we use wavelength with third peak, which is 265.4 nanometer. If the peak absorbance is below 1, then using the peak wavelength is the best. But if the peak absorbance is well above 1, we might be better off using another wavelength where the absorbance is closer to 1. The best measurement wavelength may be the one that minimizes the relative contribution of spectral interference, which may or may not be the peak maximum. Very high absorbance will cause two problems. First, the precision of measurement is poor because the concentration of the caffeine is too high and cause the transmitted intensity is so low. Secondly, the calibration curve linearity is poor due to straight line. The effect of straight line can be reduced by taking the readings at a wavelength where the absorbance is lower or by using a non-linear calibration curve fitting technique. It only measures the linear relationship between the variables. There is perfect positive relationship between two variables when correlation coefficient is equal to 1. As the different concentrations were used, different adsorbents were recorded and different calibration graphs obtained. But regardless, the equation of light still passed through the origin unless the concentrated samples were used to do the measurement. Refer to the table, we can say that the longer the brewing time, the higher the caffeine content in tea. Based on the table, the pressed coffee contains the highest concentration of caffeine and followed by instant coffee, black tea, green tea, and decaffeinated coffee. As we can see, the confidence interval of sample 3 overlap with the sample 4. The confidence interval of sample 5 overlap with the sample 1 as well. Although some samples will overlap with another sample, the results still considered confident to determine the exact type of beverage in the samples, as 95% confidence interval for this graph. Refer to this table. The highest concentration of caffeine is sample 2, then followed by sample 4, sample 3, sample 1, and sample 5. The higher the dilution factor, the lower the concentration, the lower the adsorbance. Theoretically, the samples were diluted with 10 times dilution factor, so the concentration also reduced by 10 times dilution as compared to the original samples. There were some discrepancies, such as the deviation of ideal concentration when samples were diluted.
Smudges on the cuvette, especially the clear part, can seriously impact the result because the UV light passes through the cuvette, then into the samples to measure the absorbance, but because of the impurities, they will absorb some of the UV light, giving us inaccurate results. Having insufficient sample in the cuvette can cause problems, as the light might not go through the sample because it comes in at a different level of height than the sample. The standards that were prepared for the calibration curve were at the wrong concentrations because of inaccurate dilutions, such as doing it at small volumes, can ruin the whole experiment because of an inaccurate calibration curve. The same applies to the samples as well. For equipments in a laboratory, different manufacturers have different uncertainties, and because of this, there will be slight differences in the recordings of results. Human errors might be a large contributor to errors in any experiment, and a big example of this would be parallax error because of differences in eyesight and the inability to properly gauge the meniscus level.
A low standard deviation indicates that the data points tends to be close to the mean of the set.
Cleaning the clear part of the cuvette with a chem wipe will remove any impurities that absorbs the UV light unnecessarily, giving us better results. Diluting the standards and samples at a larger volume will give more accurate concentrations and makes it easier to pipette out the amount needed for the dilutions. Using better equipment, such as a pipette that will measure out the right volume each time, makes it easier and more accurate to do dilutions. Repeating the experiment several more times can give us a better average, leading to a more accurate result. Filling the cuvette with the appropriate amount of sample will ensure that all of the UV lights passes through the sample, giving a more accurate result. There are other analytical methods that can be used to measure the concentration of a solution, such as high-performance liquid chromatography, gas chromatography, flame atomic absorption spectroscopy, and ion selective electrode. HPLC is a technique used to separate, identify, and quantify components in a mixture. It has a relatively high resolution, which gives a more accurate result. However, it's too expensive for our purposes. Another method that can be used is GC. Its typical uses include testing the purity of a substance or separating the different components of a mixture. Like the HPLC, it has a high resolution, and unfortunately, like the HPLC, it is costly to run it. Flame AAS is a technique which makes use of the atomic absorption spectrum of sample to assess the concentration of specific analytes. It is cheaper to use it, however it has a relatively low resolution and it uses up the samples, unlike the UV-Vis method. Therefore, UV-Vis method is the optimum for analyzing caffeine concentration. In conclusion, the maximum wavelength of caffeine is at 265.4 nanometers. Using a set of standards, a calibration curve was plotted, which is its absorbance versus its concentration. The calibration curve was a straight line going through the origin at a small gradient. Samples at different dilution factors were measured for their absorbance and were compared to the calibration curve to obtain their concentrations. At no dilutions, the absorbance measured were high, thus the concentrations were also high. At 10 and 50 dilution factors, however, the concentrations drastically decreased as a result of the absorbance measured being decreased. Based on the concentrations, deductions were made to find out what the samples were, either green tea, black tea, pressed coffee, instant coffee, or decaffeinated